Every year, thousands of steel frame structures are built on construction sites around the world, not for small homes, but for skyscrapers, bridges, factories, and sports arenas. Today's steel fabrication plants are not just about machines and metal. They are high-tech hubs where heavy-duty equipment pushes its limits. You will find cranes lifting hundreds of tons, robots performing precision welds, and advanced computer systems overseeing quality control. So, how are these structures made? How does the heavy machinery work, and why is every step, from metal melting to final assembly, absolutely critical? You will definitely want to see this for yourself. Steel preparation is the very first and most important step in manufacturing frame structures. At steel mills and factories, the process starts with massive metal stock delivered in the form of steel sheets, rods, or blocks, some weighing up to 50,000 pounds. These materials often arrive in specialized containers that can carry multiple tons of metal, and large overhead cranes, capable of lifting up to 100 tons, are used to move them across the facility. One of the most impressive sights is the lifting and transport of these heavy chunks of metal. The crane approaches a towering pile of steel blocks, grips them using heavy-duty hooks, and with astonishing precision, hoists them to the next stage of production. Crane operators must work in perfect sync, because even a small mistake can cause major damage or a dangerous accident. The metal blocks are usually cut down using industrial shears or plasma cutters. These specialized machines can slice through steel up to 3 inches thick in just 1 second. They create precisely shaped profiles for the next phase of production, delivering perfectly clean cuts that would be nearly impossible by hand. Once the steel has been trimmed into the required shapes, it moves on to the melting stage. This is one of the most dramatic parts of the process, as the steel is heated to over 2,800 degrees Fahrenheit, producing smoke clouds and bursts of flame. Technicians operate powerful furnaces that can process up to 300,000 pounds of metal per minute. They must keep the temperature steady, because even a small fluctuation can change the steel's properties. Once liquefied, the steel is ready to be poured into molds. At every stage of this process, quality control is key. Special computer systems track temperature, pressure, and other vital data to ensure consistency and precision. When the steel reaches its molten state, the next important step is impurity removal. Impurities like sulfur, phosphorus, and other unwanted elements can weaken the metal. To eliminate these, filtration and delivery systems go into action. They use physical filters to attract unwanted particles, or inject chemical agents that bind with them to form slag. The slag rises to the surface, where it can be easily skimmed off. At this point, large gas jets, usually nitrogen or oxygen, are introduced to further purify the steel. These jets are injected through special nozzles that help break down and disperse impurities. Once the steel is clean and cool, it moves to the rolling stage. The remaining molten metal is sent to rolling machines, where giant presses flatten it into long steel sheets. Each sheet goes through multiple rolling phases, with pressure reaching up to 10,000 tons per square inch. The finished sheets can be less than half an inch thick, depending on the needs of the structure. Next comes shaping the individual structural elements. CNC machines and heavy-duty tools cut and form the sheets and beams according to the blueprints. Computer-controlled systems allow for cuts accurate down to the millimeter. Individual elements, like beams, columns, and joints, are shaped and prepared for welding. A single machine can produce up to 500 components per day. Welding and assembly are some of the most impressive parts of building a steel frame. After the metal parts are cut and prepped, they are positioned and joined using arc welding, gas welding, or even laser welding. Heavy metal segments, weighing over 500,000 pounds each, are hoisted by cranes capable of lifting 50 to 100 tons. These cranes maneuver the sections into place using steel cables and counterweights, allowing precise placement before welding. Meanwhile, welders get to work at the center of the operation. They use machines powered by electricity or gas mixtures that can reach temperatures of over 6,500 degrees. These high temperatures allow metals to bond at the molecular level. Welders carefully guide the arc or flame to melt the edges and fuse them. The seams must be flawless, so the process demands total accuracy. After welding, every seam is rigorously inspected. Laser scanners examine the joints for cracks or flaws. Ultrasound checks are also performed to detect microscopic gaps or defects inside the welds. At the same time, other crew members install additional structural elements like beams and support frames, with precision down to the millimeter. Automated robotic systems also play a huge role. These machines position steel components and hold them in place while welders work. Once everything is welded and secured, the final steps begin: grinding and painting the joints for corrosion protection. This finishes the steel frame assembly and prepares it for transport or installation on site. For large-scale projects, this process can take weeks or even months. It is not just technically complex, it is visually stunning. Watching huge steel pieces rise and come together to form new shapes is truly amazing. Structures that must endure extreme conditions undergo additional treatment, like alloying and anti-corrosion coating. This extends their lifespan and keeps them looking good for decades. Zinc coatings or special heat-resistant paints are often used. Stress testing using pressure rigs helps engineers understand how the frame will perform under load. Computer simulations reveal weak points and allow stress to be redistributed where needed. These tests often last up to 72 hours, depending on the complexity of the structure. Finished steel components are transported to the construction site using specialized trucks and carriers. Gantry cranes capable of lifting 200 tons handle these deliveries. At the site, tower cranes and mobile cranes take over, lifting each piece into position. Assembly can take days or weeks, depending on the size and complexity of the project. As of the year 2025, approximately 135 million monitors are shipped to markets worldwide every year. This includes both new models and replacements for old ones, as part of a typical 4 to 5 year tech upgrade cycle. While it is difficult to pinpoint the exact number of monitors in global use, due to varying lifespans and growing demand, it is estimated to be in the billions. That is because as much as 66% of the global population uses computers. But what happens when it is time to recycle a monitor? Cathode ray tube monitors, those old bulky screens, were common before flat screens took over. They contain glass with high lead content, phosphors, and electronic components. Lead in the glass can make up as much as 20% of a monitor's weight. Sounds dangerous, right? Light-emitting diode, or LED monitors, are the modern flat screens that use LEDs for backlighting. They are lighter and more energy efficient, but still contain plastic, metal, and rare earth elements. Guess what? Mishandling these monitors can cause serious environmental problems. Lead from CRTs can leak into soil and water, and plastic from LEDs can take centuries to decompose. That is why recycling is not just a trend, it is a must. In the United States, over 4,400 million pounds of e-waste is generated every year, but only 25% is recycled locally. Every single day, Americans throw away more than 500,000 computers and mobile devices. This creates a massive environmental challenge. Electronic recycling centers, like Repowered in Minnesota, play a key role in addressing this issue. Each year, they process about 3 million pounds of electronics, which makes up 5% of all electronic waste collected in the state. Impressive, right? These centers accept any device with a cord, except for large appliances, and ensure proper disposal or reuse. Some states, like California, go even further. There, it is illegal to dispose of e-waste in regular landfills. California has over 600 drop-off locations, and recycling is funded through a fee on the sale of new monitors and televisions. By the way, California spans around 163,696 square miles. It is the third largest state. Trucks are loaded with old monitors and driven to recycling centers. This method is typically used for short and medium distances. For long hauls, container shipping is used. It is more cost-effective and safer for large volumes of electronics. At the plant, monitors are unloaded in the intake area, where trained staff inspect them for hazardous materials and evaluate their condition. The monitors are disassembled into key components, such as cathode ray tubes, display panels, power supplies, and other electronics. This process can be done manually or with specialized equipment. The separated parts are sorted by material type. Casings, power supplies, and other metal components are separated for further recycling. Recycling metal parts from monitors looks like a full-on industrial operation. Massive machines work in sync to turn scrap metal into something new. Shredders roar. Furnaces blaze. The air is thick with the scent of molten metal and the noise of industry. Metal components are cleaned of contaminants like paint, plastic, and other non-metallic materials. This is done with machines that strip away surface layers and boost metal quality. Rotating brush systems or dedicated surface cleaning machines are used. This step can also involve shredding, crushing, or other mechanical methods. Metals might also be treated with chemical solutions to remove corrosion and other residues, using acids or alkaline solutions to dissolve unwanted layers. Then, the metal is shredded into smaller pieces using large presses or industrial shredders. This makes it easier to process and transport. Next, metals are sorted by type. Ferrous metals are separated from non-ferrous ones. Each metal type requires a different recycling process. The metal pieces are then melted down in giant furnaces at high temperatures. Steel melts at about 2,552 degrees Fahrenheit, while aluminum melts at around 1,112 degrees Fahrenheit. As the metal melts, impurities are removed, and the material is poured into molds to form new ingots. These ingots are used to manufacture new metal products like construction materials, car parts, or home appliances. Using recycled metals cuts production costs and preserves natural resources. At smelting plants, huge conveyor lines move metal pieces through different recycling stages. Workers in full protective gear oversee the process to ensure safety and quality. Thanks to this effort, old monitors are reborn as new, useful products, helping the environment and advancing sustainability. Plastic components from monitors and other electronics are collected and sorted by type, usually polycarbonate, acrylic, and polystyrene. They are shredded into small pieces, using machines like industrial shredders or crushers. This makes the plastic easier to transport and process. The shredded plastic is then cleaned to remove contaminants and impurities. This step uses air jets, magnets, or other tools, depending on the plastic type. The clean, shredded plastic is melted and molded into pellets. These pellets become the raw material for making new plastic goods. In the United States, about 6,600,000 pounds of plastic are recycled annually. That is only around 8% of total plastic waste. But those recycled pellets go on to make more than 100 million new plastic items every year. Shredders and crushers roar as they grind plastic. Conveyor lines move the material through different stages of processing. Recycling plastic saves about 88% of the energy compared to producing new plastic from raw materials. A typical CRT monitor contains almost 3 pounds of lead in its glass. The leaded glass is separated from the monitor's other components. The cathode ray tube is disassembled into individual parts: the screen, the funnel, and the neck. The screen is made of activated glass, while the funnel holds the lead. The glass is cleaned of phosphor and other residues using chemical solutions or mechanical methods. After cleaning, the glass is homogenized. During this stage, you can see giant rotating drums scrubbing paint and resins from the surface. The glass is then sorted by size and sent off for further processing. Thanks to this method, old leaded glass gets a new life while supporting sustainable development. The glass is melted down in special furnaces at high temperatures. Lead is extracted and purified from impurities. This clean lead is used to manufacture new products like batteries, ammunition, or building materials. So yes, it is possible your old monitor might one day help protect the country. Now let us move on to recycling circuit boards. Printed circuit boards are shredded using machines like hammer mills or industrial shredders. This helps extract most of the metal content. The resulting material is usually smaller than 2 inches in size. This shredded material is passed through magnetic separators and air jets to separate metal from non-metal elements. Metals like copper, gold, and silver have unique physical properties that allow for efficient separation. Chemical extraction methods are used to recover the metals. For example, gold and silver are dissolved using acidic solutions. These solutions are then processed to obtain pure metals. Another method involves heating the circuit boards to high temperatures to burn away the non-metal materials and extract the metal content. However, this method can release toxic gases, so it is used with strict safety measures. During chemical recovery, you might see massive tanks filled with acidic solutions where metals are being separated. After extraction, the metals are purified and formed into ingots for manufacturing new goods. Through this process, old circuit boards are reborn as new, useful materials, supporting sustainability and protecting the planet. LED display panels can be recycled for use in making new screens or other electronic components. While the process is complex and not always cost-effective, it is seen as a promising path forward. Some LED monitors contain rare earth elements, which can be extracted and reused. Recycling LED monitors saves up to 70% of the energy compared to making new items from raw materials. Imagine a plant spread out over 11 million square feet, where thousands of specialists work every single day to assemble an aircraft made up of more than 4 million parts. Here, in Toulouse, France, giants of the sky are born, from the legendary A380 to the cutting-edge A350. Parts for these aircraft come in from all over the globe. Wings from Britain, the fuselage from Germany, and engines from the United States. This is not just a plant. It is the heart of European aviation and a true marvel of engineering. And now we are going to take a look inside. The Airbus plant in Toulouse covers an area of over 11 million square feet. Now, that is an impressive size for any manufacturing complex, and especially so in the aviation industry. This plant produces not only the A380, but also other aircraft models from the company, like the A350. To produce these technological wonders, Airbus uses more than 2,000 workstations equipped with the very latest technology. This plant is the heart of Airbus aircraft production and a complex logistics hub, where every stage of aircraft manufacturing is its own form of art. The Airbus plant in Toulouse was actually founded way back in 1946 under the name Aerospatiale. Initially, it was a French company specializing in aviation manufacturing, and it laid the groundwork for the future Airbus plant. All the early stages of the plant's operation involved creating aircraft for both military and commercial needs. The Toulouse plant was strategically chosen for its location, which provided convenient access to transportation and logistics routes within France and across Europe. Originally, the plant focused on developing smaller aircraft, but over time, it expanded its capacity and implemented new technologies to produce large passenger aircraft. In 1970, the company Airbus Industry was established, a consortium that brought together 4 major European aviation companies: Aerospatiale from France, Deutsche Airbus from Germany, Construcciones Aeronauticas from Spain, and Air Italia from Italy. From that point on, the history of the Toulouse plant became closely linked with the development of the aviation industry in Europe. This is where the production process for Airbus aircraft began. aircraft that would become significant competitors to giants like Boeing. Over the following decades, the Toulouse plant expanded multiple times as aircraft production really picked up speed. In the late 1980s and early 1990s, the plant became the main hub for producing aircraft like the Airbus A300, the first certified wide-body aircraft, and the A320, one of the most popular aircraft in the history of civil aviation. Over time, the Toulouse plant became the primary production center for models like the A330, the A340, and the A380, that huge double-decker aircraft that became a symbol of Airbus. In the 2000s, the Toulouse plant underwent major changes and modernization to handle the production of newer models, like the A350, which was introduced to the market in 2013. For this purpose, new assembly halls were built at the plant, including large facilities for assembly and testing, along with new automation systems to boost production efficiency and precision. Manufacturing the Airbus A380 is such a complex and detailed process that it requires innovative methods and technologies for its assembly. Just imagine, each aircraft produced at the plant consists of over 4 million individual parts. These parts are supplied from all around the world, from China to the United States. For example, the main fuselage components come from Germany, the wings from Great Britain, and the tail section from Spain. That is right, the Toulouse plant primarily handles the final assembly of the aircraft. This is standard practice for major aircraft manufacturers. Major engine manufacturers, like General Electric and Pratt & Whitney, supply the powerful jet engines for Airbus aircraft. Additionally, various aviation systems and components arrive from the United States. China is a key supplier of various metal parts, plastic components, and other materials for the aviation industry. Furthermore, Chinese companies provide certain aerodynamic parts. Other parts, including structural elements and fuselage details, are supplied by various European countries, such as Germany, Italy, Spain, and Great Britain. Well-known Canadian companies, like Bombardier, also supply components for different Airbus models, notably for the A220. After being manufactured, these parts are transported to the plant in Toulouse, where they are assembled into a single, complete unit. This often takes several weeks, and the large components are transported using specialized methods, like ships or air transport. The Airbus plant in Toulouse covers an area of 11 million square feet. It is one of the largest aviation manufacturing sites in the world. First, inside the plant's enormous assembly halls, the aircraft fuselage is put together. This is the main body of the aircraft, composed of several large segments that are delivered separately. Each fuselage segment is a major part of the structure, joined together with the others using cranes and specialized assembly machines. A crane lifts the parts, and they are carefully connected using special bolts and welding techniques. This is how the frame structure begins to take shape, although it is not yet in its final form. Once the main fuselage sections are assembled, the wings are brought into separate areas for installation. These wings are heavy, and their installation also involves the use of hydraulic cranes. When the wings are ready, they are attached to the main fuselage structure. Special attention is paid to this stage because the join between the fuselage and the wings is a critically important part that affects the aircraft's aerodynamics and safety. The installation of all the necessary systems, electrical, hydraulic, and avionics, also happens during this phase. Parts are integrated in special clean rooms to prevent any damage or contamination. This is a highly precise process, as all the elements, like cables, pipes, and computer systems, must be correctly positioned within a limited space. Robotic systems are often used at this stage for the precise placement of these elements. Once the aircraft structure is nearly complete and all internal systems are connected, it is time to install the engines. This is another critically important step, as the engines play a significant role in the aircraft's overall stability. Large hydraulic mechanisms and cranes are used to lift the heavy engines and precisely attach them to the aircraft structure. This also demands a high degree of precision and care. As soon as the aircraft is assembled and the engines are in place, it undergoes a series of tests and checks. On the ground, they conduct tests on the braking systems and check the aircraft's response to mechanical stresses. All these operations take place on enormous testing grounds, which allow for trials involving various loads and speeds. At the same time, the functionality of all the aircraft systems is verified. The testing area itself covers about 2 million square feet. After all the tests and adjustments are done, the aircraft moves on to the finishing stage, where it gets painted and the final details are added: window sealants, stripes, logos, and other design elements. Before the paint is applied, the aircraft is thoroughly cleaned to remove any contaminants, grease residues, or dust. Following this, the metal surface is treated to ensure better paint adhesion. An important step is the application of an anti-corrosion coating, which protects the aircraft body from oxidation and other harmful factors. This coating is applied using special sprays or spray guns to create a uniform protective layer. The aircraft is then painted in several layers. Most often, special polyurethane paints are used, which provide a durable, resistant coating. These are applied using rotary atomizers, which allow for even distribution of paint across the entire surface. The aircraft is placed inside a special painting hangar, sort of like a large enclosed area, where the necessary temperature and humidity levels are maintained to ensure proper paint adhesion to the surface and facilitate quick drying. After the base color is applied, a top coat is added, which provides extra protection against atmospheric elements and also gives the aircraft a glossy finish. This layer also adds resistance to ultraviolet rays, preventing the paint from fading in the sun. After painting, the aircraft are inspected for any defects. If any cracks or bubbles appear in the paint, they have to be corrected. In the final stage, airline logos or special liveries are applied to the aircraft. This might involve not just applying paint, but also installing special decals or applying a protective film to the surface. This process can take up to several weeks for a single aircraft, depending on the size and complexity of the livery. In total, painting a complete Airbus aircraft requires about 3,300 pounds of paint. The process of installing the cockpit is one of the most complex and precise operations. The aircraft cockpit, especially in models like the A350 or A380, contains hundreds of different sensors, control systems, displays, and other technical elements that must be precisely configured. Altogether, a cockpit can contain up to 5,000 different parts. Interestingly, the assembly of the cockpit takes place separately from the main aircraft body. This is done in special workshops where the cockpit is fully equipped before being transported for final integration into the aircraft. The entire cockpit installation process takes several days and demands the highest level of precision, because any malfunction in the control or navigation systems could lead to serious problems during the aircraft's operation. Another crucial aspect is the integration of avionics, which are the aircraft's electronic control systems. These systems allow pilots to monitor flight parameters, engine status, the situation in the sky, and perform other critically important functions. Installing the avionics takes anywhere from several days to several weeks, depending on the complexity and type of the aircraft. More than 10,000 people are involved in the aircraft assembly process, including engineers, technicians, testers, and other specialists. The production cost for a single A380 aircraft is around $445 million United States dollars, making this project one of the most expensive in the world of aviation. Just for the development of new technologies and the improvement of automation processes, Airbus spends millions of dollars every year. Have you ever wondered how the beer you drink is made? Imagine this: 1 million tons of grain every year, thousands of bottles filled every minute, and automated machines working with millimeter precision. We are diving into the world of brewing at the Anheuser-Busch factory, the largest beer producer in the world. We will discover how ordinary barley transforms into a hoppy beverage, and why every drop of Budweiser undergoes meticulous quality control. This is not just production. It is a spectacle of scale, flavor, and innovation that you absolutely will not want to miss. Did you know that the average American drinks about 2,500 ounces of beer annually? And while the Czech Republic and Germany lead in beer consumption, Anheuser-Busch supplies a significant portion of the global demand. It all begins with humble barley. At the factory, I witnessed how tons of grain are delivered and processed before being turned into malt, one of beer's main ingredients. Everything here is automated. Specialized machines grind the grain and soak it in water to wake up the enzymes. It literally looks like a dance of machinery, with each piece knowing its role precisely. In enormous steel tanks as tall as a 3-story building, giant machines load tons of golden barley. You can hear the soft, calming sound of the grain cascading downward, reminiscent of gentle rain. What happens next is pure technological magic. Special machines delicately grind the grain, exposing its core, starch. It looks as though the grain passes through a massive waterfall, transforming into a light, fluffy powder. This powder then ends up in enormous vats filled with warm water. Here is an interesting fact. The machines do not simply soak the grain in water. They maintain an ideal temperature and humidity level, like a steam bath designed to activate the enzymes. You can see the vats come alive with hot steam passing through them. Water mixes with the ground grain, forming a thick, creamy mixture that begins to release the aroma of freshly baked bread. This moment feels incredibly vivid. It is as if the grain awakens and starts working together with this mechanical orchestra. The malt vat begins to rotate. Yes, it does not just sit still. It practically dances, with special paddles mixing the blend so the enzymes activate evenly. Steam rises, forming a light mist that fills the room with a sweet aroma. Sometimes this steam is lit with special lamps, adding a touch of spectacle, as if you are witnessing a scene from a sci-fi movie. And this is only the beginning. The porridge then passes through other tanks equipped with precise filters that separate the liquid, the malt extract, from the leftover grain. Now imagine this happening on a scale where a single processing cycle can fill thousands of bottles of beer. This is not just production, it is a full-scale performance. The machines operate with the precision of fine jewelry, and as you stand nearby, you feel like a witness to something monumental. The entire process is filled with rhythm, aromas, and sights that will make you forever respect beer. Though, to be honest, I already respect beer because it sponsors my enjoyable Friday nights. Anheuser-Busch sources barley from various farms, and the quality is scrutinized down to the smallest detail. Different beers require different malts. Lager? A light malt base is needed. Stout? Add darker, roasted malt. You get the idea. They use around 1 million tons of grain annually for beer production. Now for the most exciting part. These giant steel fermentation tanks are so enormous that it feels like you could fit an entire football team inside one. This is where the magic begins. Maltwort, a sweet liquid extracted from the grain, is mixed with hops and yeast. Honestly, the smell in the fermentation hall is something else. It is a warm, rich aroma reminiscent of bread and fruits. The yeast here works like crazy, turning sugar into alcohol and carbon dioxide. Fermentation lasts anywhere from several days to a few weeks, depending on the type of beer. The factory employs about 4,000 people. It is like a small town. But what surprised me the most is the level of automation. People here mostly monitor the process from screens while the machines handle the bulk of the work. Even the smallest details, like the temperature and pressure inside the tanks, are controlled by computers. Honestly, the factory feels more like a scientific laboratory than a traditional brewery. And it did not start out this technologically advanced. Anheuser-Busch has an incredibly fascinating history. It all began in the year 1852, when a small brewery opened in St. Louis, simply called Bavarian Brewery. In the 1860s, it was purchased by Eberhard Anheuser, a German immigrant, and his son-in-law, Adolphus Busch, joined the business a few years later. That is when the real boom began. Adolphus Busch was not just an entrepreneur, but an innovator. Imagine this. In the year 1876, they created Budweiser, the first American lager beer. To make it accessible anywhere in the United States, Busch introduced revolutionary transportation methods, such as refrigerated rail cars. This was a game changer for the beer industry. Today, Anheuser-Busch is part of the AB InBev Corporation, the largest beer producer in the world. Their brands, Budweiser, Michelob, Stella Artois, Corona, are recognized on every continent. According to AB InBev, Budweiser alone is sold in over 85 countries, producing over 2,064 million gallons of beer annually. On average, each production line fills 1,500 bottles or cans per minute. The bottling line is a true showcase of technical perfection. Hundreds of cans and bottles flow in rapid streams, perfectly aligned, gleaming under bright lights. The entire process is fully automated, and watching it is like observing a finely tuned clock mechanism, but on an enormous scale. First, empty bottles or cans enter the conveyor. They are thoroughly washed to remove even the tiniest specks of dust, because cleanliness here is paramount. Machines spin each container under spiral nozzles that shower them with jets of water. Next comes the filling stage. Cans line up under high-precision dispensers that pour the exact amount of beer into each one in mere fractions of a second. Interestingly, this happens in near-vacuum conditions. Why? To prevent foam formation and avoid any contact between the beer and oxygen, as this could affect its flavor. The next step is sealing. Caps for bottles or lids for cans are fed onto the conveyor through a separate line, and special automatic clamps secure them with such speed that it is almost impossible to see the movement with the naked eye. Then comes the packaging. This is where the real conveyor magic happens. Bottles, cans, kegs, everything moves at lightning speed. More than 1,500 bottles are filled and sealed every minute. Watch this rhythm. Every can undergoes a seal test before moving on to packaging. Here is another interesting detail. Bottle coloring and label printing are also automated. Conveyors move, machines blink, and staff only occasionally intervene to ensure everything runs smoothly. Overall, lasers, sensors, and cameras at every stage ensure quality control. If even a single can or bottle fails to meet standards, the machine instantly removes it from the line. This guarantees that only the best product reaches consumers. Despite the scale of production, the taste of the beer remains consistent. That is their top priority. Every batch undergoes tasting before hitting the shelves. And trust me, this is not just a formality. The tasters here work at the level of true sommeliers. And this is just one factory in the Anheuser-Busch network. In total, the company operates 12 breweries in the United States, along with over 20 distribution centers. Another thing that impressed me, Anheuser-Busch actively works to reduce its environmental impact. For instance, the water used in brewing is purified and reused, and all waste, such as grain husks, is sent to farms as livestock feed. You can now tell your spouse, "Honey, I am not just drinking beer, I am supporting cattle feed in the United States. If you survive saying that, let me know how it goes." Although their largest factories are in the United States, the company has facilities on every continent except Antarctica. By the way, the factory in St. Louis is also a tourist attraction. Every year, they host tours for tens of thousands of visitors. Guests are taken to historic production halls, shown giant tanks, and even get to see their famous Clydesdale horses. And if you are wondering whether you can taste the beer, of course. At the end of each tour, guests are invited to a tasting room to sample the freshest beer. Anheuser-Busch is not just a company, it is a living history of innovation, scale, and tradition. They started as a small brewery in St. Louis and have grown into a giant that is reshaping the beer industry. Next time you open a bottle of Budweiser or Michelob, remember these numbers, this scale, and the people behind every drop of beer. Imagine this, a house printed in just 24 hours. Sounds like science fiction, right? But it's real. Back in 2018, the United States saw its very first 3D printed house. Today, there are hundreds of these homes, and the numbers keep growing. This technology doesn't just build houses, it's redefining architecture with designs that are both stunning and efficient. And the best part? A home like this could cost as little as $10,000. Ready to see how a giant printer turns concrete into cozy living spaces? Let's dive in. The first 3D printed house in the US appeared in 2018. Now, there are hundreds of these homes, and the count is steadily climbing. Let's start with the basics. 3D printing is a technology that creates objects layer by layer using specific materials. When it comes to houses, this means a massive 3D printer extrudes concrete or other construction materials based on a pre-designed blueprint. Think of squeezing frosting from a piping bag, except instead of frosting, it's concrete, and instead of a cake, it's a fully functional house. These 3D printers are no small feat. They're massive. Imagine a structure the size of a small crane or a garage hangar. For example, Icon, a Texas-based company, uses a system called Vulcan. This printer stands about 11 feet tall and spans over 32 feet in width. Its modular design allows it to expand and adapt to the size of the house being built. The printer operates on rails or special platforms, moving around the construction site. That's why it can print anything from a tiny cottage to a spacious home. Essentially, it's like a large truck, a smart, precise machine that gets the job done with remarkable accuracy. Let me tell you about my visit to one of these construction sites. Icon, based in Texas, invited me to see their house printing process up close. And let me tell you, watching this gigantic printer in action makes you feel like the future is already here. It all begins with architects designing the house on a computer. It's like those 3D renderings you've seen in movies or on designer websites. Depending on the complexity of the design, creating a 3D model can take anywhere from a few hours to several weeks. A simple, single-story house without elaborate details might only take a day or two, but a complex project with unique shapes, energy-efficient features, or intricate interiors, that's a whole different ballgame. Here, architects work closely with engineers to ensure everything checks out. Will the walls hold up under pressure? Are the windows and doors positioned correctly? Are the local climate conditions accounted for? The coolest part? Modern software like AutoCAD, Revit, or SketchUp makes this process faster and allows for detailed visualization of every inch of the house. At the construction site, a massive 3D printer is set up. This printer, essentially a giant robot, moves on rails or with manipulators. It starts printing the house layer by layer. The main material? A special quick-drying concrete that becomes incredibly strong. Once the walls are done, the roof, windows, doors, and other elements are added. At this stage, traditional construction methods are used to finish the house. While the printer can handle the main structure, components like the roof, windows, and doors are typically crafted from traditional materials like wood or metal. For example, the roof might be made of metal or wood, depending on the project. Windows and doors are also custom ordered and installed using conventional construction techniques. This blend of innovative technology and proven materials ensures homes that are not only efficient, but also comfortable to live in. The entire process takes anywhere from a few days to a few weeks, a stark contrast to traditional construction, which can drag on for months. 3D printed homes have a ton of advantages, making them an increasingly popular choice. For starters, they can be built in just a matter of days. These houses are also significantly cheaper than traditional ones. According to Icon, a small home can cost as little as $10,000. And the designs? They're nothing short of art. This technology also minimizes waste and uses eco-friendly materials. Traditional construction often leads to a lot of leftover materials like concrete, wood, and metal, especially when cutting pieces for doors, windows, or walls. But with a 3D printer, materials are used only where needed. The printer lays down each layer precisely according to the design, leaving no excess material behind. It's not just about efficiency, it's about sustainability too. Many companies involved in 3D construction use materials that have a lower environmental impact. For instance, the concrete might include recycled components or be made with eco-friendlier ingredients, reducing pollution during production. Moreover, precise material calculations mean fewer resources are consumed, eliminating the need for extra stock or creating waste that ends up in landfills. This approach not only saves money, but also significantly reduces the environmental footprint of construction. The technology also opens doors to new types of eco-friendly materials, such as biodegradable concrete that incorporates recycled waste or organic substances. These materials reduce CO2 emissions and the need for extracting new resources. So, 3D printing isn't just speeding up construction, it's making it more sustainable and environmentally friendly. It's not just a trend, it's a real shift in the construction industry, one that could greatly improve our ecological outlook for years to come. Of course, it's not all perfect. The technology is still new and comes with its challenges. Currently, most 3D printed homes are made of concrete. But for more complex designs, new materials will need to be developed. These massive printers are also hard to transport and require specific conditions to operate. Plus, many countries don't yet have clear regulations for constructing such homes. Icon can print a house in just 24 hours. One driving factor behind this technology is its potential to address affordable housing shortages. 3D printing dramatically cuts costs on materials and labor. For example, Icon is working on a project to build homes for low-income families at just $4,000 each. The technology also unlocks incredible possibilities for architects. A 3D printer can create intricate, unconventional shapes that are almost impossible with traditional methods. Architects now have the freedom to design without limits, knowing the printer can handle any form or detail. The future of 3D printed homes looks incredibly bright. These technologies are already being used not just for housing, but also for offices, schools, and even hospitals. Icon is building the first fully 3D printed neighborhoods, including a project in the US in 2021 that delivered 5 homes to financially struggling families. And here's what blew my mind. Icon is working with NASA to print homes on Mars. Imagine that. One day, people might live in 3D printed houses not just on Earth, but on other planets too. Icon was founded in 2017 in Austin, Texas, by a group of engineers and entrepreneurs. Their goal was ambitious, yet simple: to create technology that makes housing fast, affordable, and sustainable, especially for those with limited access to traditional homes. The idea came when the founders realized the construction industry was bogged down by outdated methods and high costs for materials and labor. They envisioned 3D printing as a way to simplify the process, lower costs, and provide homes for those in need. Initially, Icon started as a small startup in the construction sector. It quickly gained traction and attracted major investments. Soon, Icon partnered with the Bjarke Ingels Group to create a groundbreaking 3D printed house, marking a significant milestone in the industry. This was the first house printed using technology that reduced material and labor costs. From there, they scaled up to build larger homes for various social programs. In the following years, Icon secured significant funding from venture capital firms, allowing them to improve their technology and expand production. For instance, in 2020, the company raised $35 million, enabling them to grow their operations and launch new projects. Think batteries are just boxes that store power? What if I told you it takes nearly 375 tons of rock and over 528,000 gallons of water to produce a single electric vehicle battery? Or that 70% of the world's cobalt is mined under terrible conditions, sometimes by children? In this video, you'll learn not just how lead-acid and lithium-ion batteries are made, but also the environmental impact they leave behind. Ready for some shocking facts that will change the way you see batteries? Let's get started. Car batteries are the heart of modern vehicles. They power the engine start, fuel electrical systems, and in the case of hybrids or electric vehicles, are the primary energy source for motion. But let's dive into their origins. The story of batteries begins back in the 18th century. In 1800, Italian scientist Alessandro Volta invented the first chemical battery, known as the voltaic pile, a far cry from the rechargeable batteries we know today. The first rechargeable batteries were created by French physicist Gaston Planté in 1859. These were lead-acid batteries, and remarkably, they're still widely used in vehicles with internal combustion engines today. The modern production of car batteries is a complex, multi-step process that requires precision and strict quality control. Let's break down the details using the most popular types: lead-acid and lithium-ion batteries. For lead-acid batteries, the primary materials include lead, lead dioxide, sulfuric acid as the electrolyte, and polypropylene for the casing. Lead is either mined from ore or recovered from used batteries. It's then purified and melted for further use. Recovering lead from old batteries is a process that combines engineering expertise with a touch of modern-day alchemy. First, old batteries are dismantled, crushed in specialized machines, and sorted into lead, plastic, and electrolyte components. Think of it as a high-tech blender that breaks everything down into its core ingredients. The lead components are sent to smelting furnaces, where they're heated to temperatures exceeding 1,100 degrees Fahrenheit. At this stage, the metal transforms into a shiny silver stream that's mesmerizing to watch. Impurities and slag are separated, leaving behind pure lead, ready for new uses. The purified molten lead is poured into molds, where it cools and solidifies into perfectly uniform ingots. These ingots form the foundation for new batteries. The most fascinating part? This lead can be recycled endlessly. It has already lived in previous generations of batteries and might just end up powering your car. Lithium-ion batteries are made from key components like lithium, nickel, cobalt, manganese, graphite, and an electrolyte. Lithium is sourced either from salt flats in South American countries like Chile and Argentina, or from ore deposits in Australia. For lead-acid batteries, the electrodes are crafted from lead plates coated with active materials, specifically lead powder and lead dioxide. Picture this. Molten lead is poured into molds or rolled into thin sheets, which are then cut into precise shapes. These plates often feature multiple holes or grids to enhance bonding with the active material. The active material, which coats the grids, is prepared as a thick paste made from lead powder, water, sulfuric acid, and additives that enhance the chemical reactions. Let's take a closer look. The powder is produced by oxidizing lead in specialized mills, which grind it into a fine dust with the required properties. Watch as the grids move seamlessly along an automated conveyor, where the paste is applied to both sides. Rollers in the machine press the paste into the grids with just the right amount of force, ensuring even coverage and deep penetration into the cells. Excess paste is scraped off with blades, leaving a perfectly smooth layer. These paste-coated grids are then sent into special drying chambers. Inside, the paste loses moisture and hardens, transforming into the active material. We've covered lead-acid batteries. Now let me show you how lithium-ion batteries are made. In lithium-ion batteries, the anodes are made from graphite, while the cathodes are crafted from metal oxides, like lithium cobalt oxide. Next comes the assembly of the battery cells. These are the basic building blocks of the battery. In lead-acid batteries, cells are made by stacking several plates separated by separators. In lithium-ion batteries, the cells can be cylindrical, prismatic, or in pouch cell form. Electrolyte filling is the next step. In lead-acid batteries, a sulfuric acid solution is poured in. For lithium-ion batteries, an electrolyte made from organic solvents ensures the transfer of ions between the electrodes. The finished batteries undergo an initial charge to activate the chemical reactions. Each battery is tested to ensure it meets key parameters such as voltage, capacity, and resistance to discharge. Lead-acid batteries are then encased in polypropylene shells. Lithium-ion batteries, on the other hand, are often assembled into modules, which are later integrated into large battery packs for electric vehicles. Battery production is an energy-intensive process with significant environmental impacts. While lead can be smelted and reused, plastic casings are recycled into new shells, and the electrolyte is neutralized or processed. The situation with lithium-ion batteries, however, is far more challenging. Only about 5% of lithium-ion batteries are recycled. This is due to the complexity of extracting lithium, nickel, and cobalt. But the damage doesn't stop with neutralizing the components. To produce a lithium-ion battery for an electric vehicle weighing about 1,100 pounds, it takes 550,000 pounds of rock and nearly 530,000 gallons of water. This depletes Earth's precious resources. Producing just one EV battery generates anywhere from 3 to 16 tons of carbon dioxide. Imagine that. This is the same amount a gas-powered car emits over 5 years of driving. And that's just from one battery. The most troubling issue, however, is cobalt mining. About 70% of the world's cobalt comes from the Democratic Republic of Congo, where workers, including children, labor under horrific conditions. According to Amnesty International, more than 40,000 children are involved in cobalt mining. To make matters worse, mining often destroys local ecosystems, leaving lasting environmental damage. Recycling lead-acid batteries in countries with low environmental oversight, such as India and China, presents its own set of dangers. Lead dust and acid emissions often escape into the air, creating toxic clouds that harm the health of hundreds of thousands of people. Have you ever wondered how many times aluminum can be recycled? Imagine this. One can you drank from today could be back on the shelf as a brand new can in just 60 days. And here's a jaw-dropper. Over 120,000 aluminum cans are used every minute worldwide. But wait, there's more. In the United States alone, enough cans are recycled each year to cover 3,000 football fields. Why is recycling aluminum so critical? How do these tiny metal heroes make such a massive impact on the planet? Let's dive into this video where every statistic amazes, and the transformation process will leave you inspired. The journey of recycling aluminum cans starts with collection, a crucial step in the recycling chain because timely gathering of raw materials ensures efficient processing later on. Most aluminum cans are collected through specialized waste collection systems in cities and communities. Many countries have waste sorting programs encouraging consumers to deposit empty cans in dedicated metal recycling bins. In the United States, there are widespread redemption centers where consumers can return used cans for a small cash reward or discount, incentivizing eco-friendly behavior. These programs are also common in parts of Europe and Australia. Some regions even organize campaigns where individuals can bring used cans to special recycling stations, making it easier to gather metal waste while reducing environmental pollution. Globally, about 120,000 aluminum cans are used every single minute, a staggering number that highlights the importance of efficient recycling. Many stores feature special bins for collecting empty aluminum cans, especially in areas with popular deposit systems where consumers can return packaging for a refund, often earning a few cents for each can. Beverage manufacturers and packaging companies also participate in the recycling process by sending metal waste from production to collection centers. This applies to used cans and leftover aluminum elements from the manufacturing process. Some recycling systems even include automatic waste sorting at the collection stage. Advanced technologies like magnetic separators are used to extract aluminum from other metals and plastics efficiently. In regions without such systems, manual sorting is still the norm. In the United States, the aluminum can recycling market is valued at over $1 billion annually. This massive industry injects revenue back into the economy, fueling businesses that recycle and produce new products from repurposed metal. Once collected and sorted, the cans are transported to a recycling facility, where they're stored in massive containers or warehouses until processing begins. The entire recycling journey of an aluminum can take less than 60 days, from the moment it arrives at the facility to the moment it's transformed into a brand new product. That means the can you finished today could be back on the shelf in just 2 months. To ensure a smooth process, cans must be kept separate from other waste materials, so they're often stored separately. Before moving on to further processing, the cans undergo a thorough cleaning. This includes washing off any leftover liquids, removing labels, adhesives, and other contaminants that might still be on the packaging. And now for the most epic part, shredding. Once cleaned, the cans are shredded into small pieces using industrial shredders or other mechanical equipment. This step drastically reduces the volume of the material, making it easier to process. What's left are aluminum shreds, or chunks, ready to be transformed into new products. I've got to say, being there for this part was nerve-wracking. It felt like one of those shards might fly off and hit me in the eye. And the noise, the grinding and crunching were absolutely deafening. Hot. Insanely, blisteringly hot. That's how it felt when we approached the smelting furnace. The shredded aluminum pieces are sent straight into it. 1,220 degrees Fahrenheit, a temperature so intense, it's surprising it's not 1,222 for some devilish symmetry. Melting is the key stage where the metal is heated until it turns liquid. During this process, any remaining impurities and other materials are burned away, leaving behind pure aluminum ready for reuse. Watching it felt like witnessing the Terminator's final moments. I swear. The team explained to me that smelting is energy intensive, but even with the high energy consumption, this process is far more efficient and less costly than extracting virgin aluminum from ore. The molten aluminum from the furnace is poured into molds to create ingots, wire rods, or sheet metal. These aluminum ingots, known as slabs, are massive blocks that are easy to handle during later processing stages. Each slab measures several yards in length and about 2 feet thick. Once cooled and solidified, this metal is ready for a new life, whether as fresh aluminum cans, car parts, construction materials, or other products. Here's the incredible part. This process can be repeated endlessly. Aluminum can be recycled over and over without losing its quality. Imagine that. Cans can go through the recycling loop dozens, even hundreds of times. It doesn't wear out from remelting. Honestly, it feels like we were lied to. Terminator had to be made of aluminum, folks. Now, what are these wire rods, you ask? Fair question, and I've got the answer for you. Wire rods are a form of aluminum created after the molten metal is poured and shaped into thin wires or rods. After smelting, the liquid aluminum is cast into molds for further processing. The metal is rolled into large wire rods using specialized rolling mills. These mills reduce the cross-section of the metal and shape it into the desired form by passing it through rollers. The rods can then be cut into smaller sections or sent off for additional processing to create a variety of aluminum products. In the end, wire rods are the foundational form of aluminum used to manufacture new products. This keeps the recycling and reuse cycle going strong. The diameter of aluminum rods can vary depending on their intended purpose, typically ranging from 0.04 of an inch to 0.75 of an inch. However, this can change based on production specifications and the final application. Thin wire rods, with a diameter ranging from 0.04 to 1/10 of an inch, are commonly used to make wires, electrical cables, or delicate metal components. Medium wire rods, measuring 1/16 to 0.4 of an inch, are suitable for sturdier products like structural elements or, in some cases, new aluminum cans, when further processing requires that specific diameter. Thick wire rods, over 0.4 of an inch in diameter, are reserved for heavy-duty applications such as the automotive industry or the production of large structural components. Each type of wire rod has its own specifications and undergoes additional processing depending on the final aluminum product being manufactured. To produce aluminum sheets, the slabs are gently heated and passed through powerful rolling mills that flatten them into thin sheets. At this stage, the sheets measure about 1/4 to 2/5 of an inch thick, but they're still too thick for most applications. After hot rolling, the sheets are cooled to stabilize their structure. If needed, they undergo annealing, a controlled process of heating and slow cooling, to relieve internal stress and improve the metal's flexibility. For ultra-thin sheets, like foil or packaging materials, the aluminum goes through cold rolling, reducing its thickness to less than 0.04 of an inch. This precision ensures the sheets meet the requirements for various specialized applications. Once the aluminum is formed into the required shape, whether as wire rods or sheets, it's transported to factories or directly to customers for further use in manufacturing. Recycling aluminum requires significantly less energy compared to extracting new material from ore. In fact, recycling aluminum saves up to 95% of the energy that would otherwise be needed for mining and processing raw aluminum. To put it into perspective, it's like a 100-watt light bulb running for 4 hours. Here's another mind-blowing stat. If all the aluminum cans recycled in the United States each year were stacked end to end, they'd cover approximately 3,000 football fields. And if you combined the recycled cans from the US and Europe, they could wrap around the Earth twice. Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material. Stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact, old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning, the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term. A gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. Water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila, a new product appears, the packaging for your favorite smoothie or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. Ready to explode with curiosity? In this video, we're about to open some top-secret doors to the world of fireworks and firecrackers, things you never even knew existed. Stick around, and you'll see how a simple blend of gunpowder turns into the magic behind the brightest blasts. You'll get the lowdown on the wild history behind their creation and the unusual secrets of master pyrotechnicians. This segment will get your heart pounding faster, trust me. Watch till the end, because the best part is still ahead. Stay with us all the way through, and you'll find out something that'll totally flip your perspective. Don't miss out. Firecrackers, they're the more hot-headed guys in this family. Their main trick? It's all about the sound, not the show. Sure, they're simpler in design, but they deliver the same kind of magic. Noise and pure adrenaline. Like fireworks, firecrackers use black powder as their base, but the approach here is a bit more straightforward. The key is nailing the right balance to get a powerful boom without any extra fancy effects. Typically, a firecracker contains a black powder mixture, a casing, and a fuse. We'll get into what's inside later, but for now, let's talk about the casing. It's usually a paper or cardboard cylinder that holds everything together. The material's gotta be strong enough to hold off the blast till the big moment, but not so tough that it creates dangerous shrapnel. The fuse is the most critical part. It sets off the entire explosive process. It could be a thin cotton wick soaked in chemicals or more modern ignition systems. How are firecrackers made? All the ingredients for the black powder mix are measured out with serious precision, then blended to get the perfect consistency. Accuracy is huge here. Just a little extra saltpeter can make the explosion go wild. Too little, and the firecracker won't ignite at all. Paper or cardboard tubes are cut to the needed length, then carefully loaded with the black powder mixture. These casings typically have sealed ends to build up just the right pressure for the explosion. At the top of the firecracker, a small hole is made for the fuse. The fuse is inserted and held in place with glue or a special sealant. The bottom and top edges of the firecracker are sealed tightly, often using glue or heat bonding. This ensures safe storage and transportation. Next, the firecrackers undergo careful testing. Manufacturers check the sound level, ignition speed, and quality of the explosion. Not all firecrackers are created equal. Cheap ones often have uneven filling, weaker sound, and a bigger risk of misfiring. They use lower quality materials, like plain paper instead of sturdier cardboard. High-quality firecracker casings are made from sturdy yet lightweight material. The black powder mixture inside is evenly distributed for a consistent effect. The fuses have a precise burn time to give you enough seconds to back off to a safe distance. Making firecrackers is no joke. Pyrotechnics plants follow strict safety rules. Workers operate in small crews, wear anti-static clothing, and handle only minimal amounts of mixture at any one time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question comes up a lot. The deal is, a firecracker's explosion isn't just a chemical reaction. It's a massive release of energy in a confined space. When the powder burns, it releases hot gases that expand super fast, creating a powerful shockwave. And since the casing is tightly packed, that wave comes with the trademark boom sound we all know. The word firecracker comes from the French pétard, meaning a blast. Like fireworks, firecrackers trace their roots back to China. Initially, they were used to scare off evil spirits, and only later did they become a popular form of entertainment. Today, firecrackers are an essential part of many celebrations and festivals around the globe. But their history shows that even the simplest things can have deep roots and a fascinating evolution. So, the next time you hear that familiar bang, remember just how much skill, history, and technique is packed into each tiny firecracker. When it comes to making fireworks, you also start by mixing gunpowder with other components. If you think of gunpowder as the engine of the firework, then the other materials are the artists who create that explosion of color, light, and shape. To get bright sparks, you need metal powders like aluminum, magnesium, and titanium shavings. For vivid colors, you rely on metal salts such as strontium, barium, copper, and sodium. To boost the energy of the blast, you add ingredients like potassium nitrate, perchlorates, and charcoal. These act as oxidizers and fuels. And to hold it all together, you use binding agents, like water-soluble glues. Each component is first ground into the finest possible powder. Picture shining metal particles dancing in the light as the master prepares them for blending. These powders are so lightweight, it's almost as if they're suspended in midair, like some kind of magical dust. The most important step starts when the ingredients go into a mill filled with ceramic or wooden balls. These balls rotate gently, grinding the mix into a perfectly uniform blend. There's a soft rustle and a light tapping sound, kind of a subtle rhythm, reminding you that a future burst of colors is being born. As for mixing the ingredients by hand, at traditional production sites, this step is done with great care and reverence. Specialists slowly and carefully blend the ingredients with wooden or copper paddles. Why so slow? Because even a single stray spark could set the whole thing off. The mixture looks like a shimmering sand, where each component has its role to play. To avoid accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds a sort of mysterious alchemy, as gunpowder and colorants form tiny granules. The smallest mistake can cause a tragedy. You know what pyrotechnic masters do before they start working? They remove all metal objects, even wedding rings, to prevent sparks. In many labs, cell phones are strictly forbidden, and employees wear anti-static clothing. Even the air matters. Conditions are kept humid enough so that mixes don't dry out and become dangerously volatile. Before packing the mixture into the casing, the masters test how it burns. A small sample is ignited, and everyone holds their breath. Is that the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors. That's the coolest part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged. These are tiny pellets with a special composition. Where'd those brilliant reds, greens, and blues come from? All thanks to chemical compounds. For instance, barium makes green, strontium makes red, and copper makes blue. Once all the components are prepped, the next crucial step is filling the casing, where the heart of the future firework is born. It's right here that the explosive mix and colorants become a finished product, capable of painting the night sky in every color of the rainbow. The casing is a shell that holds all the fireworks parts together. It's made from special materials that can handle high pressure and heat, yet remain light enough to shoot into the sky. Cylindrical shapes are perfect for forming sharp patterns like rings, chrysanthemums, or peonies, while spherical shells create symmetrical three-dimensional effects, like a glowing orb exploding into hundreds of sparks. The filling process is super important, because the exact placement of components ensures the desired effect. Let's break it down step by step. First, you take cylindrical or spherical shells, usually made of cardboard, plastic, or specially treated paper with fire-resistant properties. Spheres typically come in two halves that will be joined later. It's crucial that the casing is airtight. That guarantees the explosion happens at the right moment with the right intensity. The black powder charge, acting as the main engine, sits at the center. It's responsible for propelling the firework skyward and making sure it explodes properly. Around that charge, the colorants and special effect mixtures are arranged. Each tiny star element is placed by hand or using special machines. These stars are what we call the pellets that burn in the sky. For spherical shells, these stars are placed evenly, so that when it explodes, it forms a perfect sphere of light. In cylindrical shells, charges are often laid in layers or formed into specific patterns, depending on the planned effect. One standard spherical firework can hold about 200 to 300 pellets. Large, multi-layer shells might have over 1,000 of them. To ensure the firework explodes at the right time, a time delay fuse is added, a small tube filled with a slower burning composition. This timer connects to the main charge, providing a delay between the rocket's launch and the burst in the sky. After all elements are in place, they're secured with a special paste or paper spacers. This keeps every component locked in position during the launch. The casing might then be wound tightly with string or glued for extra rigidity. Crafting one large professional-grade firework can take up to 4 hours, considering all the careful assembly and testing. For a massive show with several thousand shells, pyrotechnicians might work for a few months straight. The spherical shape is the classic standard in pyrotechnics, giving an even spread of stars and creating that perfect circular effect. Filling such a shell requires even more skill. Each star is placed by hand around the central charge. It's all on the master's shoulders. How the components are arranged will define how the explosion looks. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the powder ignites, those pellets spread out just right, forming the intended pattern. Every year, over 200,000 short tons of fireworks are produced worldwide. China is the leader here, accounting for about 90% of the global output. For major holidays, like Independence Day in the United States or New Year's Eve in Sydney, up to 10,000 separate fireworks might be launched in a single night. Such a display can last over 20 minutes and sometimes costs as much as $5 million. Despite the beauty of fireworks, safety stats are pretty alarming. In the United States each year, up to 10,000 injuries are reported due to improper use of pyrotechnics, with about 70% of the injured being young people under 20 years old. Every year, the world produces over 420,000 tons of snails. That's more than the weight of 300,000 cars. Imagine these slow creatures being transformed into delicacies worth up to 50 euros per kilogram, or their slime being used in cosmetics priced at up to 300 euros a jar. Snail farming isn't just a business, it's a billion-dollar industry. Want to know all the secrets? Stick around till the end. Picture vast fields where thousands of tiny snails crawl slowly among the greenery. These are snail farms, and they're more than just a thing. They're a serious business. Europe leads the world in snail farming, with most farms located in France, Italy, Spain, and Poland. The main species grown here are the Helix aspersa, or small gray snail, and Helix pomatia, known as the Burgundy snail. The idea of farming snails has ancient roots, dating back to ancient Rome. Think about it. The Romans were both gourmets and innovators. They were the first to cultivate snails on a large scale for food. How did it work? Romans built special snail gardens where they kept snails, feeding them herbs, fruits, and even wine. Yes, you read that right. They literally soaked snails in wine to make them more tender and flavorful. The famous Roman naturalist Pliny the Elder, who lived in the 1st century AD, wrote about snails being a delicacy at noble banquets. He even mentioned a Roman gourmet, Quintus Fulvius Lupinus, who established the first known snail farm in the 1st century BC. After the fall of the Roman Empire, snail farming was somewhat forgotten. But during medieval times, monks revived it. For them, snails were a convenient food option during Lent, as they weren't officially considered meat. Clever monks, huh? By the 19th century, snail farms gained popularity in France and Italy, where modern farming methods were developed. The French were the first to turn snails into a gastronomic brand now known as escargot. In the 20th century, snail consumption increased so much that industrial-scale farms became necessary. Today, we have entire industries, from food to cosmetics, all thanks to this ancient Roman idea. Isn't that fascinating? Every year, over 420,000 tons of snails are farmed globally, with Europe dominating the market. France, for instance, consumes about 30,000 tons of snails annually, half of which are imported. Imagine the scale. Let's start with the snail nursery. Farms begin by collecting snail eggs, those tiny white pearl-like balls. The eggs are carefully selected because the farm's success depends on their quality. To encourage breeding, farms create specific conditions. The air temperature must be around 70 degrees Fahrenheit, with nearly 100% humidity. It's like a paradise for snails. Farmers even use special systems to keep the air moist, ensuring the snails' comfort. The eggs are then moved to incubators, where tiny snails hatch a few weeks later, barely recognizable as the future delicacies. Surprising, isn't it? My friend once had pet snails, and they bred like crazy in any conditions. But here, with all this care, there are no guarantees. Perfection is truly the enemy of good enough. Let's take a closer look at how snails grow. Once they hatch, the snails are moved to open enclosures, special fenced areas on the farm where they can crawl freely. They're fed a mix of grains and vegetables like cabbage, carrots, or even lettuce. Snail care is a science. Farmers regularly check their health, provide plenty of water, and even protect them from natural predators like birds or insects. Fun fact, a snail can drink more water than its body weight. In some countries, snail farms play relaxing music to reduce stress. Snails can take up to 6 months to grow large enough for harvest. Their size and weight depend on the species and farming conditions. Harvesting snails is an art. When snails reach the right size, they are collected, often by hand. Each snail is carefully inspected to ensure it's healthy and high quality. In snail farming, healthy and high quality involves several key factors: physical condition, suitability for consumption, or cosmetic use. A healthy snail actively moves, stretches its body, and responds quickly to stimuli like touch. Sluggish or closed snails might be stressed or sick. Their shells must be intact, free of cracks, spots, or chips, a sign of sufficient calcium in their diet. Healthy snails should also show no signs of parasites, fungal infections, or diseases that could affect their viability. On average, a snail weighs about 1 pound, though the ideal weight varies by species. This is the optimal size for culinary use. Before processing, snails are kept without food for 3 to 5 days to clear their digestive systems, ensuring the product is safe. A snail's diet impacts the quality of its meat, so their meals consist of greens, fruits, and special mixes. High-quality snails have tender, slightly sweet meat. They must be raised without harmful pesticides or fertilizers, as they are highly sensitive to contamination. For cosmetic purposes, snails need to produce a sufficient amount of slime, known as mucin. But more on that later. This requires proper nutrition and farming conditions. Healthy snail slime is transparent, impurity-free, and rich in beneficial components like allantoin, elastin, collagen, and vitamins. Quality snails live for 3 to 5 years, which is crucial for sustainable production. However, on farms, they're usually kept for about 14 months. Modern snail farming emphasizes eco-friendly practices, no soil or water contamination, and an organic approach to feeding. A healthy, high-quality snail grows in ideal conditions, eats a balanced diet, and shows no signs of stress or illness. It's perfect for gourmet dishes or premium cosmetics. Collected snails are washed and sent for further processing. If the farm caters to the restaurant market, the snails are immediately placed in special refrigerators, where they enter a state of dormancy, a natural process allowing them to sleep. Globally, over 420,000 tons of snails are farmed each year, with France, Italy, Spain, and Greece being major producers. Snails move at less than half a pound per second, so to cross a football field, they'd need about 5 hours. But they can endure a 2-hour walk in the rain without a break, the equivalent of a marathon for us. An average farm raises anywhere from 100,000 to 1 million snails. Now, the exciting part. How do these slow creatures become delicacies? First, they're prepped for consumption, washed, cleaned, and boiled. Then, they're marinated, baked, or stuffed with delicious sauces. Did you know French restaurants love serving snails in their shells with a garlic butter sauce? It's their signature move. If food is clear, how did snails end up in cosmetics? It's all about the slime. It contains beneficial substances like allantoin, collagen, and glycolic acid that work wonders on the skin. In ancient Rome, slaves rubbed snail slime on their mistress's skin, believing it healed wounds and rejuvenated. In the 1980s, Chilean farmers raising snails for export noticed their hands became unusually soft, free of cuts or scars. This sparked the idea of using mucin in cosmetics. On specialized farms, snails are kept in comfortable conditions where they produce slime. This slime is harvested without harming the animals and used in creams, masks, and serums. They say this ingredient works miracles, rejuvenating skin and addressing imperfections. The snail slime cosmetics industry is worth $760 million and grows 10% annually. The biggest buyer, South Korea. The slime collection process may seem odd, but it's designed to be cruelty-free. There are two methods: manual stimulation and automated systems. In manual stimulation, farmers gently massage the snail's body or spray it with clean water and sea salt. The snail secretes slime as a natural defense mechanism. The collected slime is washed and sent for filtration. For automated systems, large farms use special devices. Snails are placed in containers where they are gently stimulated with water or air streams. The slime flows into a reservoir for collection. Afterward, the snails are washed and returned to their enclosures. They can produce slime again after a few days, ensuring the process doesn't harm them. The collected slime is purified, leaving only the valuable components. The resulting mucin is rich in collagen, elastin, glycoproteins, and other active ingredients. After processing, the slime becomes a raw material for cosmetics or pharmaceuticals. Snail slime is then used in high-end creams and serums that repair skin and treat acne. To produce 33 ounces of quality mucin, about 50,000 snails are needed. The snail market isn't just about food or cosmetics. In the European Union alone, it's a multi-billion euro business. 1 kilogram of snails can cost between 20 and 50 euros, depending on their origin and processing. Cosmetic products made from snail slime sell for 30 to 300 euros per jar. How do 15,000 gallons of milk turn into butter? Why was it once as valuable as gold? And why do modern artists sculpt masterpieces from it? This process isn't just physics, it's pure magic. Magic that transforms everyday essentials into something indispensable. Ready for a journey that'll change how you see butter forever? Let's dive in. So, our story begins with cows. Picture this. Farmers milking cows, and that fresh milk heads to the factory in specialized tanker trucks. One tanker can hold about 15,000 gallons of milk. These trucks are airtight and refrigerated to keep the milk fresh during the journey. Fun fact: demand for organic butter has risen by 13% in the last 5 years, as consumers lean towards eco-friendly options. It takes about 19 to 24 quarts of milk to make just 2 pounds of butter. The most expensive butter in the world? It's made from Yakutian cow milk and costs over $200 per kilogram. Surprising, right? Every country has its own butter-making traditions. For example, in Tibet, they use yak milk to make butter, not just for food but also for temple lamps. Now, when the milk arrives at the factory, the first thing it goes through is quality control. It's tested for fat content, protein levels, cleanliness, and even the absence of antibiotics. If everything checks out, it's poured into massive stainless steel tanks, where it waits for processing. And now for the magic. Well, technically, it's physics, but let's be honest. It looks magical. The milk is loaded into a separator, a machine spinning at mind-blowing speeds. Think of it as a giant centrifuge that spins the milk to separate the lighter cream from the denser skim milk. In the end, you get two products, cream and skim milk. The cream, that's what we need for butter. And the skim milk? It's used to make other products like yogurt or cheese. Butter was first mentioned over 4,000 years ago in Sumerian cuneiform texts. Back then, it wasn't eaten. It was used as a skin ointment or even in religious rituals. In fact, butter is also mentioned in the Bible. In the book of Genesis, Abraham serves his guests butter from the herd. For the Vikings, butter was so precious they used it as currency. They stored it in huge wooden barrels, and it was even considered a status symbol. Makes you wonder how they kept it from spoiling, right? Fast forward to today, the United States produces about 2 million tons of butter annually, making it one of the largest butter producers in the world. States like California, Wisconsin, and Idaho lead the way with massive dairy farms. The cream is heated in special pasteurizers, like a heat tunnel, where it's quickly brought to 160 degrees Fahrenheit and then cooled again. Why? To kill harmful bacteria while preserving the taste and nutrients. Once cooled, the cream moves to the next stage, the exciting part. Here's where the real action starts. Special machines begin churning the cream. Imagine a giant mixer. At first, the cream thickens, resembling whipped cream used in desserts. Before the 18th century, butter was churned manually using wooden barrels or clay pots. Mechanized churners didn't appear until the 1870s, making butter production much easier. As the churning continues, the fat clumps into small balls, forming butter. The liquid that separates during this process is buttermilk. And no, it's not wasted. It's used in baking or even as a drink. The butter starts to look familiar, but is still just a clump of fats. We're about to change that. Now the butter goes into special machines that knead it. This step makes the butter smooth and creamy. At this point, salt may be added to make salted butter. Fun fact, salted butter lasts longer because the salt acts as a natural preservative. In the US, people consume about 4.5 billion pounds of butter annually. During World War II, butter was in such short supply that margarine and substitutes became popular. But after the war, butter made a comeback thanks to its natural taste. Today, butter sales in the US amount to about $3.7 billion, and this market is expected to keep growing. Finally, the home stretch. The butter is cooled to the right temperature and sent to molding machines. These machines give it the perfect shape, just like the bricks you see in stores. Everything's automated from here. A robot picks up the butter brick, wraps it in foil or paper, and places it on the conveyor belt. Each pack goes through one last quality check to ensure perfection. The finished butter is stored in massive refrigerators, waiting for its journey to supermarkets, and eventually to your fridge. The US doesn't just produce butter, it exports it too. This year alone, over 46,000 tons of butter were shipped to countries like Mexico, Canada, and Japan. Butter sales peak during the fall and winter holidays. Think Thanksgiving and Christmas, when everyone's baking. During the holiday season, Americans buy about 25% of the entire year's butter supply. In the restaurant industry, butter is indispensable. Restaurants across the US use over 500,000 tons of butter annually. Chains like Starbucks, Panera Bread, and McDonald's rely on butter for their baked goods and dishes. These numbers prove that butter remains a staple in American cuisine, despite the rise of alternatives. The largest butter sculpture in the world? It was made in the US at a festival in Illinois in 2017. It weighed over 2,006 pounds and was used to create a detailed sculpture. That year, the festival theme was farming, so the sculpture depicted a farm scene, cows, farmers, and even farming equipment. Isn't that wasteful, you might think? Not at all. Sculptors use butter that's no longer fit for consumption to avoid food waste. Butter has the perfect texture and density for sculpting. Artists work in refrigerated rooms, kept at 40 degrees Fahrenheit to prevent the butter from melting. They start with a metal frame for support, then layer the butter and shape it using tools like knives and spatulas. To make the sculptures realistic, they even add tiny details like animal fur or folds in clothing. These sculptures don't last long. After the festival, the butter is either recycled or sent to biogas plants, where it's turned into clean energy. This way, butter art gets a second life, contributing to sustainability. And Illinois isn't alone. Similar butter sculptures are featured at festivals in Iowa, Ohio, and other states. Butter, it's not just food, it's art. A medium for creativity and a true reflection of talent. You wouldn't believe how much technology goes into making ordinary toilet paper. Robots cutting trees with laser precision, machines rolling them out at speeds of hundreds of miles per hour, and even artificial intelligence monitoring every single inch for quality. After this video, you'll never look at toilet paper the same way again. Watch till the end. It's going to blow your mind. Let's dive right in. The process starts at logging sites, where machines known as harvesters are used. These impressive machines cut down trees, strip them of branches, and chop them into logs of precise lengths, all in one go. Honestly, I could use something this multifunctional for cleaning my house. Logging is meticulously planned, using GPS and GIS to identify optimal areas for cutting while adhering to strict environmental standards. Trees are harvested selectively to prevent over-deforestation. Logs are then transported to pulp mills by specialized trucks equipped with GPS trackers that optimize delivery routes. Alongside fresh wood, these factories also use recycled paper, collected through recycling programs, delivered as compacted bales. At the mills, the logs are fed into automated lines, where they're chipped into small, uniform pieces. See how tiny these chips are? That's thanks to industrial-grade chipping machines, equipped with sensors to control wood size. These chips are moved along automated conveyors to massive digesters. Before entering the digester, the chips pass through magnetic separators to remove any metal and sieves that ensure uniform size. Sensors and computer systems manage every stage. Inside the digester, the chips are mixed with chemical solutions like caustic soda and sulfides, a process called the Kraft method. Automated dispensers precisely measure and add chemicals based on the type of wood being processed. Feeling the heat yet? Inside the digester, the chips are heated under high pressure for several hours. This entire process is automated. Computer systems carefully control temperature, pressure, and cooking time to produce the perfect consistency of pulp, a mixture of solid particles and liquid. Now, check this out. The pulp is pumped into centrifuges, which remove heavy impurities like stones, sand, or metal. Chemicals are then added to break down any remaining linin, the substance that binds wood cells together. Advanced sensors monitor temperature, pressure, and chemical concentrations to achieve optimal pulp brightness without wasting reagents. After this, the pulp is washed to remove residual chemicals and byproducts. Multi-stage washing systems clean and recycle water, minimizing waste. Oh, you're still here? Great. Quick story. One Halloween, I was completely swamped with deadlines. Instead of competing in our neighborhood's annual Best Holiday Decorations contest, I gave up. In a moment of pure laziness, I TP'd my own house, just like in those classic prankster movies. Surprisingly, it got more compliments than any decor I'd ever done. The irony, right? Anyway, back to business. Once purified and bleached, the pulp, which now has a creamy consistency, is piped to forming machines. Sensors installed in these pipes monitor temperature, moisture levels, and pulp density. The pulp is spread onto a forming table, the core component of the paper-making machine. This section consists of an endless wire mesh moving at speeds of up to 63 miles per hour. The pulp is evenly distributed onto the mesh through nozzles, and excess water is removed immediately using vacuum pumps. The sheet then moves to the press section, where special rollers covered with silicone or rubber squeeze out more moisture. Next up, drying. The sheet passes through a giant cylinder known as the Yankee dryer, heated to temperatures between 240 and 300 degrees Fahrenheit. By the end of this stage, the paper's moisture level drops to around 5%. Sensors constantly monitor the cylinder's temperature and rotation speed to prevent overheating or overdrying. Now for the finishing touches. The dried sheet undergoes embossing, where textured patterns are pressed onto its surface. This step enhances the paper's softness, absorbency, and appearance. Steel or rubber rollers with intricate designs create these patterns. Automated systems ensure the patterns are crisp and evenly applied. Some manufacturers add fragrances or moisturizing agents at this stage, spraying them on in thin layers using advanced nozzles. Optical and ultrasonic scanners monitor parameters like thickness, density, and uniformity. If defects such as tears or uneven textures are detected, the system automatically adjusts or discards the flawed section. Data from all scanners is fed into a central computer, analyzing the entire line's performance in real time. It can even predict potential issues, like roller wear, and notify operators for maintenance. Cool, right? After forming and drying, the paper is rolled into massive jumbo rolls. These rolls can measure several feet wide and weigh hundreds of pounds. Robotic arms transport the jumbo rolls to the rewinding section, where the sheet is unrolled, smoothed, and prepped for cutting. Rewinding machines stretch the paper and roll it onto cardboard cores, which are automatically fed into the line. Check this out. These machines can wind hundreds of rolls per minute, and they're constantly monitored for tension or defects. If something's off, the system pauses to prevent waste. Once rewound, the rolls move to the cutting section. Here, larger rolls are sliced into smaller, standard-sized rolls using high-speed cutting machines. Titanium or steel-coated blades ensure clean, precise cuts without damaging the paper. These machines operate with millimeter precision, guaranteeing uniformity. Automated systems monitor blade sharpness, replacing dull blades without interrupting the process. Each roll undergoes final inspections via high-resolution cameras and infrared sensors, checking diameter, density, and cut quality. Defective rolls are swiftly removed using pneumatic arms. Finally, the finished rolls head to the packaging section. Robotic systems handle them without contact, reducing contamination risks. Sensors align the rolls before they enter the wrapping machine, while a computer system ensures all rolls meet size and weight standards. The rolls are grouped into packs, 4, 6, 12, or even 24, based on consumer demand. Robotic arms stack and wrap the rolls using either thin but durable plastic film or eco-friendly paper packaging. This ensures protection from moisture and dirt while catering to environmentally conscious buyers. Hey bro! Today, we're diving headfirst into the wild world of money. Straight to the US Bureau of Engraving and Printing. That's the spot where real deal dollars are born. The ones that end up in people's pockets and keep the global economy humming. But listen, these aren't just some random pieces of paper with numbers slapped on them. Every bill is a legit masterpiece, packed with cutting-edge tech. We're about to uncover the secrets behind that one-of-a-kind paper, the mind-blowing microscopic details, and the top-tier security features that make the dollar untouchable. You ready? Let's roll. This is gonna be epic. First off, forget about regular paper. Dollars are printed on some next-level stuff made by Crane and Company. This isn't your basic white office paper. It's a cotton linen blend with a unique texture that's totally different from the usual. That's why dollars have that crisp crinkle and last way longer. The material is 75% cotton and 25% linen, with tiny colored fibers woven in that you can only spot under a microscope. Plus, the paper is packed with watermarks and embedded security threads, making it nearly impossible to fake. This paper gets delivered in massive rolls, each one guarded like it's gold. And boom, that's step one in the battle against counterfeiters. Now we're stepping into the engraving department, the place where the magic happens and the main design for each bill is born. This is where artists, known as engravers, carve out the intricate designs and portraits by hand on metal plates with jaw-dropping precision. Take those iconic presidential portraits, like George Washington on the $1 bill or Benjamin Franklin on the $100 bill. They're painstakingly recreated from photographs. And those lines that look straight? They're actually made up of microscopic details. That's another layer of protection. No regular printers pulling that off. Feeling a little outclassed? Don't sweat it. This stuff is straight up genius. Next up, we're heading into the heart of the factory, where the real magic of printing goes down. Check out those massive printing machines using the intaglio technique. That's fancy talk for deep engraving. Here's how it works. The metal plates made by the engravers are coated with ink, and then the excess is wiped off, leaving the ink only in the engraved grooves. The paper is then pressed onto the plate under insane pressure, transferring the ink onto it. Thanks to intaglio printing, certain features on the bills, like the portraits, have a raised texture you can actually feel. How cool is that touchable detail? This process happens multiple times because dollars are printed in layers. First comes the black ink, then green, and finally, other security features are added. Every year, they crank out about 7 billion bills here, with 95% replacing old or worn-out cash. Oh, and the ink? It's so tough that even if you bury a dollar bill for 20 years, you'd still be able to recognize it. In today's world, where counterfeiters are getting slicker by the day, money has to level up with serious protection. For instance, there's microprinting, tiny text you can only see with a magnifying glass, added around portraits or borders of bills. It's so small and detailed, it's practically impossible to fake. Then there are those special security threads embedded in the paper. Under ultraviolet light, these threads glow in different colors depending on the bill's value. For example, $5 glow blue, while $100 shine pink. And let's not forget the $100 bill. It's loaded with high-tech features like 3D holograms that shift and change depending on the angle you look at them. How's that for next-level security? Next stop, the offset printing section. This is where those background images, like the green and golden hues you see on dollars, are added. It's the second line of defense. Intricate patterns and color gradients that are almost impossible to replicate with basic tools. Rolls of future cash spin on cylinders, feeding into the printing machine. Once the ink is applied, the rolls are cut into sheets of the perfect size. Fun fact, a dollar bill lasts on average 5 to 8 years before it's retired. On the back of the $1 bill, you've got the pyramid symbolizing strength and durability, while the all-seeing eye represents divine protection. Pretty wild, right? Let's keep this tour moving. Bro, now we're in the room where dollars get their names. This is where each bill gets its unique serial number, printed in either black or green ink. It's basically the ID code for every single banknote. The next step? Stamping the Federal Reserve Seal. These seals show which of the 12 Federal Reserve banks issued the note. This whole process happens on high-speed printing machines that churn out thousands of bills per minute. And get this, the printing conditions are no joke. The machines apply 80 tons of pressure, and the wax-based ink is literally baked into the paper under high heat. The ink is specially designed to resist wear and tear, even something as wild as going through the wash. Oh, and here's a crazy stat. The total value of all cash dollars in circulation is over 2 trillion. How's that for some money talk? Before dollars leave the factory, they go through some hardcore quality control. High-tech scanners check every single bill for defects. Blurry ink, damaged paper, or misaligned designs. If there's any mistake, the bill is pulled out of circulation immediately. The ones that pass, they're neatly packed into stacks of 100 bills. The final step is packing the money. These stacks are loaded into special containers and shipped off to Federal Reserve banks. From there, they make their way to commercial banks and eventually into people's hands. The whole transportation process is locked down tight, with heavy security. We're talking millions of dollars here after all. When a bill is declared too worn out, it gets destroyed. Don't get teary-eyed, bro. Let's check out how it happens. Worn-out banknotes are tossed into industrial shredders that chop them into tiny bits. According to the Federal Reserve, around 5 billion bills are shredded every year, mostly $1 and $5 notes, since they take the hardest beating from daily use. But shredded cash doesn't just get thrown away. The Federal Reserve is big on keeping things eco-friendly, so they find ways to repurpose the materials. Here's a funny story. One time in Texas, some clueless criminal broke into a Federal Reserve facility, thinking he'd hit the motherlode. Instead of stacks of cash, though, he walked off with a giant bag of shredded money. Thinking he'd scored big, he dragged his loot home. Spoiler alert, shredded cash is worth zilch. The guy got caught within a day. Tough luck for him, but at least we got a good laugh out of it. In some states, shredded bills are pressed into dense briquettes that are used as fuel for energy production. Pretty cool, right? This process replaces wood or coal, cutting down on environmental harm. In areas with the right tech, the shredded cash can even be turned into compost, since cotton linen paper is biodegradable. Yeah, money literally gets buried in the ground. A portion of the shredded banknotes is also repurposed into souvenirs. For example, they're packed into clear balls or boxes and sold to tourists at gift shops in the Bureau of Engraving and Printing. It's a unique way to hold a piece of money history in your hand. So, how about it, bro? Want to snag a chunk of chopped up cash for your shelf? Destroying large sums of cash is a whole other level of operation. When entire series of banknotes are pulled from circulation due to design updates or new security features, the disposal process gets even more intense. The old bills are transported in armored vehicles under strict surveillance, and every step of the destruction process is carefully documented to make sure not a single bill ends up in the wrong hands. This massive operation is actually cost-effective in the long run. For instance, according to the Federal Reserve, the cost of destroying a single bill is just 0.03 of a cent, thanks to automation. Every day, up to 200 tons of banknotes are shredded across the US. Even the machines used to destroy bills are guarded as tightly as the money still in circulation. It's a big deal, but hey, with that kind of precision, counterfeiters don't stand a chance. When it comes to durability, $1 bills last about 6.5 years on average, while $100 bills can stay in circulation for up to 22 years since they're handled less often. Not bad, bro, especially when you compare it to the lifespan of large denomination euro bills, which is only about 5 years. So, how do they decide when it's time to retire a bill? That's where the Federal Reserve's specialized machines come in. These machines assess the condition of banknotes and flag the ones too worn for circulation. But here's the kicker, the actual disposal doesn't happen at the same place as the printing. The Bureau of Engraving and Printing only destroys defective bills that pop up during production. For example, if the ink isn't applied evenly or the paper gets damaged, those bills are immediately shredded. Quality control on point, right? A few years back, a group of criminals in the US decided to rob an armored truck carrying cash. They planned the heist down to the last detail, but they picked the wrong moment to strike. Instead of shiny, fresh bills, the truck was hauling worn-out banknotes headed for destruction. The plan might have seemed genius at first, but the payoff? Practically worthless. Talk about a major flop. Then there's the classic case of the thief who tried to snatch some cash from a bank. In his rush to get out, he grabbed a bag full of bills, completely clueless that it was rigged with die packs. The second he stepped out of the bank, boom! The capsule exploded, covering both the cash and the crook in bright, unmistakable dye. Those bills became totally useless, and the mastermind left a literal trail of evidence straight to where the cops nabbed him. Honestly, I bet that trail wasn't just bright red or purple. There was probably a little brown in the mix too. Not that the press would mention that part.